So up to this part we have discussed these things. Now let us proceed further, let us go further and see exactly how many types of data structure we are going to study in this course. Mainly we will be focusing our data structures discussion on the classification of data structures. So what exactly is the classification given to this data structure? So a data structure can be classified in two broad categories. The first category is called as a primitive data structure, that is a data structure which is primitively or primarily or which is already present or given to you for use. And second is non-primitive data structure, that is called as user defined data structure, we can say in a way. So what are primitive data structures? Your integer, float, characters and pointers, all these are your, which you have already studied, all these are your primitive data structure. So let us just focus our discussion on non-primitive data structures. The non-primitive data structures are again classified in two categories, that is linear data structures and non-linear data structures. Now these linear data structures are categorized in four types, that is arrays, linked lists, stacks and queues, and this non-linear data structure is categorized in three broad types, trees, graphs and skip list. Mind well, we are going to discuss the data structures only with respect to the syllabus which is given to us by university. So apart from these, various other data structures also do exist, but for this course we are going to focus our discussion on only these data structures. Now let us one by one see what exactly these data structures mean and what exactly these data structures do. Now linear and non-linear data structure, these two words are self-explanatory. First thing, linear means where the organization of data is in a single row or a linear form or in sequential memory locations. What is non-linear data structure? Again, name says the same thing. The organization or the placement of data is in non-linear form or in non-sequential memory locations. In linear data structure, the data is present in a single line, whereas in non-linear data structure, data is present in layers or in levels, only graphically speaking. The linear data structures have various different applications like arrays, linked lists, stacks and queues, whereas non-linear data structure have various applications like trees, graph and skip list. Now before proceeding further, let us just see what exactly is the difference between linear and non-linear data structure. Now if I talk about memory allocation, linear data structure has a sequential memory allocation, whereas a non-linear data structure has a layer wise or a non-sequential memory allocation. In most of the non-linear data structure, the data is placed according to the relationship present in the existing data. That simply means the next or new data element which is to be inserted in new data structure will be based or can be based on the data which is already present in data structure. For example, in BST, if I am talking about binary search trees, if I want to insert a new node, then I have to compare it with root. If it is less than root or smaller than root, then I will go to left subtree. If it is greater than root, then I will go to right subtree. So that means insertion of new thing or a deletion of new thing is based on existing data element present. So that is dependency based data structure. So memory allotment wise, linear data structure is mostly independent, collection of independent unit, whereas in non-linear data structure it is mostly dependency based. Okay. Next, if I talk about memory utilization, then in linear data structure memory utilization is inefficient, whereas in non-linear data structure memory utilization is efficient. Now to understand this, let me give you an example which I will be quoting again when I will be discussing arrays. I will be repeating this example again for linked list as well. So let me just briefly see what is exactly inefficient memory utilization in linear data structures. We know that if I declare an array of size 10, I get 10 memory locations. If I say int ARR square bracket 10 semicolon, that simply means I have declared an ARR array of type integer of size 10. So what will happen? 20 bytes, size of integer is 2, so 2 into 10, 20 bytes will be allotted to ARR. Sequentially those 20 bytes array will be allotted to ARR, correct? So in those 20 bytes I can store 10 different integers. What if I want to store 11th integer after 10 integers? It is not possible, correct? So this problem is called as overflow problem. The size, the data after the size is not accessible, correct? What if in that 20 byte memory location I store only 2 integers? So for rest of the 8 integer, 8 multiplied by 2, that is 16. 16 bytes of memory is not allotted to some other construct, and array itself is not using it, correct? That means that 16 byte is wasted. So that problem is called as an underflow problem. So memory utilization wise, linear data structure, if I consider array as an example, it has two drawbacks, that is underflow problem and overflow problem. Whereas if we discuss something about non-linear data structure, it uses memory effectively. That means layer wise, if you are storing, for each layer there are various different sections present, and you can store the memory layer wise in more efficient way. We will be seeing this thing when we proceed with the upcoming units. Then if I talk about direct access, then direct access to the linear data structure is simpler, and direct access to non-linear data structure is bit complicated. With respect to traversal, I am discussing this thing. If I want to access some element in linear data structure, then it will be a simpler thing. Whereas if I want to access some entity in non-linear data structure, I'll have to go through various different steps. That is the simply meaning of direct access. Another point of differentiation is architecture. In single linear data structure, the architecture is single level, whereas in non-linear data structure, architecture is multi-leveled. If I talk about implementation, linear data structure uses sequential memory, so implementation is quite simpler. A simple loop or mostly a pair of loop is used for data storing, data retrieval and all those things in linear data structure, whereas the process of storage, retrieval and manipulation of data in non-linear data structure is bit fuzzy, bit complicated. Not difficult, different, but bit complicated. By using a simple loop it cannot work. So you have to be bit more precise for accessing values in non-linear data structure implementational wise. The traversal means accessing each and every data element from start to end. So if I have an array, then printing all those arrays or accessing all values from start to end is a quite simple thing. Simply by using a loop you can do it. That is, traversal is by using single run. Whereas if you talk about non-linear data structure, that is skip list or trees or graph, then you might have more than one traversal ways or more than one traversal sequences or more than one traversal techniques. So that might be possible. Then time complexity wise, if I differentiate these things, then it is directly proportional to size, and it often remains unchanged when, or it changes slowly in case of non-linear data structure. Now this point is a very important point with respect to examinations. What exactly is time complexity? Now this time complexity we will be discussing again in our next topic, that is analysis of algorithm. But just for the sake of discussion, I am telling you that time complexity is amount of time required for an execution of an algorithm in broad terms. So with respect to linear data structure, if I create an algorithm to implement these data structures, time required for implementation of that algorithm is directly proportional to size. That means as a data in your data structure increases, the algorithm will take more and more time for its manipulation or for its effective execution. That is directly proportional to size. If the data size is less in your data structure, then algorithm might take less time. If the data size is more, then algorithm might take more time. It is as simple as that. It is not a case in non-linear data structure. It often remains unchanged. That means even if you improve or even if you increase the size of data, even if you store more elements to a data structure, in most of the cases time complexity remains the same or it changes very gradually. So that is the difference between linear and non-linear data structure. Normally in examination a question is asked to differentiate between these two things. So accordingly, if you write for based on these 7 points, so more than 6 marks you can very easily fetch. Of course, this is a point wise table given to you. You have to be more elaborate discussing these things. Now whenever we discuss about data structure, we have to set some ground rules. That whenever I am saying that I am discussing about array data structure, or I am discussing about a linked list data structure, or I am discussing about stack, queues, trees, graph, or any other type of data structure, I should discuss every data structure, each and every data structure based on some parameters. So which are the parameters through which I will be discussing those data structure are these parameters. I will be creating a data structure first. I will be creating an additive for it. Of course, additive will be discussing further. I will be creating an abstract data type for it. I will be creating, or I will be giving a method for selecting an individual object out of it. I will be giving you a method for updating the data structure, for what should I say, um, appending a data, or importing a data in the data structure, or insertion of data, let us just say in simple terms. Then I should give a logic for searching the data, whether that data is present or not, or if that data is present, then where exactly that is present, and what is the time required for retrieval of that data. For that I need to give algorithm. Then I need to sort the data present in the data structure. That means I need to give logic for sorting. Then I need to give logic for merging. In most of the data structure, merging is possible. It is not possible in all data structures, or even if it is possible, we don't do it with respect to our syllabus. Our syllabus, merging of two data structures is out of the bound for this syllabus. Then I need to give an algorithm to destroy a data structure or delete a data structure, or whatever memory I have allocated, I need to deallocate that memory. So I need to give algorithms, or I need to give procedures for these rubrics, these parameters, for discussing each and every data structure, whether it is a stack, whether it is a queue or a linked list or a circular queue, whatever it is. I need to create it, I need to insert it, I need to update it, I need to append it, I need to delete it, I need to search it, I need to sort it. So these parameters, based on these parameters, I will be discussing all the operations of data structures. Now let us just go through the various basic ideas or various basic data structures which we are going to study in upcoming units. In upcoming units, we are going to study something about arrays. We all know what exactly array is. In this figure, you can see that my array name is A. The size of array I have assumed as n. So this A square bracket n, which is a heading given to your table array, is array name with size n. I have assumed size to be n, and I have assumed first few elements in that array. What are the data element present in an array? 169, 196, 225, 256, 289 and 324. These are first few data elements which are present in array. How do you access these data elements? You simply access the data element based on index I, correct? So if I takes values from 0, 1, 2, 3, 4, 5 and so on, then A of I, A of 0 is first value, A of 1 is second value, A of 2 is third value, A of 3 is next value, A of 4 is next value, and so on. So whatever value of index you are having, based on that value of index, you can access the actual value present in an array. As simple as that. Now let us just combine this thing with the concept of pointers which we have studied previously. We know that what is a pointer? Pointer is a variable which stores an address, correct? Now if pointer is a variable which stores an address, then we can address your array with respect to a pointer, of course, correct? So we are going to address our pointer with respect to p pointer, correct? What is p? P is a pointer which stores address of an array. And what address of an array p stores? P stores the base address of an array or starting address of an array. In our case, 2510 is a base address of an array, so p stores 2510, correct? What if I do p plus 1? See, normal arithmetic and pointer arithmetic are different. So if I do p plus 1, that simply means I am incrementing value of pointer with size of integer. Size of integer is 2 byte, let us assume. So if I do p plus 1, so 2510 is added 2 with it, size of integer, and next value I get is 2512. Then again, if I add 1 to it, I get 2514. If I add 1 to it, I get 2516, and so on. So these are the range of addresses which can be accessed through p. And how do I access actual value? By using value at operator, so star p. So star p means value at p, value at 2510, that is 169. Value at p plus 1 will be next value, value at p plus 2 will be next value. So accordingly we access the values. So this is how we implement arrays. Then we have discussed two major problems in array, underflow and overflow. Now to eliminate those two problems, we propose a new data structure, a new linear data structure, that is called as a linked list. What is a linked list? Linked list is based on individual element. That means to store every individual element, I create a node. And what is a node? Node is a combination of two things. First, data portion, and second, variable for pointer, that is address to next location. So whenever I want to insert a node, I'll insert a single value based on its data and I'll manipulate its pointer or link portion of that data or an address portion of that data. In linked list, every node points to the next node present in the list. If it is a first node, it points to second node. If it is a second node, it points to the third node. If it is a last node, then the link portion or an address portion of last node is null. Correct? So this architecture is given so that overflow and underflow problems can be addressed. Now this architectural problem solves overflow problem. How? If you want to add more element, just add a single node. Correct? If you want to, as you are not allocating the memory for linked list beforehand, that solves automatically, that solves your underflow problem. Correct? So such a type of architecture or such type of linked list solves our arrays overflow underflow problem. So the problem of previous data structure became the advantage of this data structure. But is this data structure perfect? No, this data structure is also not perfect. There are various lacunas in it. You have only one directional access, you cannot turn back, then you cannot revert back, access the previous element. So there are various issues related to it. As the size goes on increasing, the searching will take more and more time likewise. So then we move on to the various different data structures, but let us not discuss that thing. Let us see another linear data structure, that is a stack. A simple implementation of stack can be seen by a closed-ended pipe. Let us just assume this gray pipe as a closed-ended, one-end closed pipe, correct? So whatever you insert from the top, and whatever you delete from the top, correct? So whatever element you insert will be deleted very last if you insert more elements out of it. For example, let me give you examples which is more relevant to you. I think most of you have seen girls wearing bangles, correct? The way in which they put on bangles is the complete opposite of the way in which they retrieve it. For example, if a girl puts on a red bangle first, green bangle second, and a yellow bangle in third place, then while removing, she removes yellow bangle first, green second, and red last. That means the sequence in which the insertion took place is the exact opposite of sequence in which the deletion took place, correct? So it is simple array implementation or a linked implementation of a stack. Stack is a concept, it is not an implementational base. You can implement a stack by using an array, you can implement a stack by using a linked list as well. It is simply a discipline which is given to arrays, or it is simply a discipline which is given to a linked list through which we can access the data elements. Normally applications of stack includes recursive calls of a function and parameter processing or expression checking. We will be seeing those things in upcoming lectures. Another data structure which is a bit modification of stack is a pipe which is open at both ends. Line which you might have seen at movie theaters, ticket counter, that can be given as an example of a queue. You have to be in a line at end, and when you process completely, you have to leave the line from front after taking tickets. So insertion is from end and deletion is from front. This data structure is again a linear data structure wherein sequentially all elements are placed, and again this data structure can also be implemented by using a linked list or a array or an array, correct? Now let us go to some non-linear data structures. Your family tree, that means your grandfather, then your father, uncles, then their siblings, then their children, and all those things. So such thing, if you try to represent graphically, this type of architecture is present. This architecture is called as a tree. Now in trees also there are various different types of trees. A general tree is there, binary tree is there, binary search tree is there. Every tree has some add-on disciplines to it, and everybody knows with respect to discipline there comes a responsibility, and a discipline, as we know that a disciplined person is better than undisciplined person, a disciplined data structure is better than non-disciplined data structure. So we will be adding disciplines to it, we will be imparting some rules for insertion and deletion, and we will be creating various different trees. Of course, there are red-black trees, there are height balance trees, there are AVL trees and whatnot. We will be seeing and searching those trees in upcoming lectures. Another interesting thing which we are going to study in this syllabus is graph. A graph is nothing but a tree, but a tree does not contain a cycle, graph does or may contain a cycle. Now where do exactly we see an application of graph? In Google Maps, where the nodes or ABCD which you see here, they can be your places to visit, and the blue lines connecting those places can be paths. So accordingly you can create a map by using a graph. Now what operations it can give you? A simplest route a map can give, or an effective route from one point to all nodes it can give, or the cost of each route it can give, minimum cost spanning tree it can give, and whatnot. So based on these data structures, actual real life implementation has been done. So we are going to study these architectures. Surprisingly, after learning all these architecture, then only we can learn a new data structure that is called as a skip list, which is a combination of linear and non-linear data structure. That simply means the data is arranged linearly but level wise, correct? So unless and until we understand what exactly linear data structure is, unless and until we completely understand what exactly trees are, we cannot understand the core of skip lists. So even if the skip list is given in unit number 3, we will be taking skip list after we finish our trees implementation, correct? This implementation is supposed to be the best implementation if our syllabus is concerned, complexity wise or efficiency wise. So as far as this is concerned, what we have seen in this portion of lecture, we have seen about data, data types, we have seen about various different data structures, and we have seen about the implementation or applications of data structure, or how data structure looks like, correct? So we are going to stop here at this point. Thank you for patiently listening to it.